Good morning, one and all. Good morning, one and all. Today we will going to discuss about the antenna array part second. In the part second, first we try to understand the binomial, and my next video we try to understand it, the Dolphin-Chebyshev type of the array. First, advantages of the linear array with the non-uniform amplitude distribution. The most of the often meet the broadside arrays are classified according to type of their excitation amplitudes. First, the uniform broadside array is a relatively high directivity, but the side lobes level are high. So you try to understand what is the difference between the uniform broadside array and binomial broadside array and the Dolphin-Chebyshev type of the broadside arrays. Basically, the uniform BSA is a relatively high directivity, but the side lobe levels are high. In Dolphin-Chebyshev type of the broadside array, for given directivity with a fixed number of the array element and which achieves the lowest side lobe levels, and in case of the broadside array which does not have a good directivity but has very low side lobe levels, when the distance between the two isotropic point sources d, which is equal to lambda by 2, there is no side lobes at all. Then binomial broadside array. The binomial broadside array was invented and proposed by J.S. Stoney second to synthesis pattern without side lobe, and first consider a two element array along the z-axis. But we know that every antenna should be placed along the z-axis because we want that the radiation is the maximum in the vertical direction. Then the element of an array are identical and their excitations are same. The array factor is in the form of the array factor which is equal to 1 plus z, where z which is equal to e raised to z psi, and psi which is equal to kd cos theta plus beta. This is the equation number 15.7 from Balnis. If the spacing between the antenna is a d, is a less than equal to lambda by 2, and beta which is equal to 0, that is the broadside array. The array factor has no side lobes at all, and this will be provided. The array factor square which is equal to 1 plus cos phi square plus sin square psi, and by mathematically we have to be equivalent to 1 plus cos psi which is equal to 4 cos square psi by 2, where psi which is equal to kd cos theta, and the first null of the array factor is obtained from 15.8, and which is given by 1 by 2 pi by lambda, that is the beta should be provided d cos theta 1 2 which is equal to plus minus pi by 2, and theta array factor for 1 2 which is equal to plus minus cos inverse of lambda upon 2d. Then as long as the lambda d is less than lambda by 2, then first null does not exist. Then if the d is a lambda by 2, then your theta of array factor 1 2 which is equal to 0 and 180 degree, and this is visible range of the theta for all secondary lobes are to limited. Then second, consider the two element array whose elements are identical and same as the array given above, and the distance between the two array is again d. Then in case of the binomial broadside array, this is the new array has the array factor of in the form, that is the array factor which is equal to 1 plus z plus 1 plus z, and once we have to be expanding 1 plus z and 1 plus z which is equal to 1 plus 2z plus z square. This is the equation, next equation number 15.10. Since the 1 plus z has a no side lobes, so 1 plus z having the no side lobes, there is a no question the 1 plus z square does not have any side lobes. So continues this process for an element array produces, and for array factor should be defined 1 plus z raised to n minus 1, and which is given by the equation number 15.11. If the d is less than equal to lambda by 2, then the array factor does not have any side lobe regardless of the number of the elements n, and the excitation amplitude distribution and can be obtained easily by using the Pascal triangle. Then how to form the Pascal triangle when we have seen for this example. For here there is a reference point 1. Here I have taken the one reference point, and this triangle should be expanding for the n number. Then 1 is taken as the reference. For this case 1 is taken as the reference here from the left side triangle, and 1 is taken as the reference for the right hand triangle. Then for the third row element, how we have to be 1, 2 and 1 should be formed. Then 1 will be taken as the reference, 1 plus 1, 2 is taken here, and 1 is again taken for the right hand side. Then here if you have to be able to observe that there is this 1, 1, 1, 1, 1 up to the till at the extreme left side, all the first element should be 1 because 1 is taken as the reference, and for the right hand side all the elements are 1 because 1 is again taken as the reference, and to form the Pascal triangle. This is the Pascal triangle. Okay, then we come here, actually our point. Then 1 is taken as the reference, then 1 plus 2 is the 3, 2 plus 1 is the 3, and 1 is taken as a 1. Then for the next row, 1 is taken as the reference, 1 plus 3 is a 4, 3 plus 3 is a 6, 3 plus 1 is a 4, and 1 is taken as the reference. Then again 1 is taken as the reference, 1 plus 4 is the 5, 4 plus 6 is the 10, 6 plus 4 is the 10, 4 plus 1 is the 5, and 1 is taken as the reference. And these are the relative excitation amplitudes for the each element of the n plus 1 element array can be determined. And this the binomial distribution of the excitation of the amplitude, which is called as the binomial array. Okay, then for here we have to find out the radiation pattern and the directivity. Its half power beamwidth for the binomial array is given by the isotopic point sources 1 and 2 having separated by the distance lambda by 2. HPBW is approximately equal to 1.75 upon square root of L upon lambda, where L is the n minus 1d is the array element, and to find out this radiation pattern having the number of the binomial array is 10. Then we have to find out the directivity. The directivity is find out by using this equation T0, which is equal to 1.77 under root of n. Okay, then I hope that all of you understand the binomial array, binomial side array, and this binomial array we have to be able to find out how it will be able to define, how it will be represented, to construct on mathematically to find out finally HPBW relative to its directivity, its radiation pattern, its Pascal triangle, and binomial, why it is called as the binomial side array. I hope that all of you understand my concept behind of the binomial side array. Thanks for watching my video. Please subscribe my channel and contact at the given email ID. For my next video we have understand and we will going to discuss about the Dolphy-Chebyshev type of the array antenna. Thank you.